Hi. Let's talk about representing integers as sequences of bits. Starting with just 8 bits, which is a standard byte. If we have all 8 bits set to 0, then this simply represents a number 0. And then we have a positional binary system, where the first bit is going to mean 1, and the second bit is going to mean 2. If we set them both to 1, then this is 2 plus 1, that is 3. And the third bit is 4, and so on. We can continue this until we reach the point where all bits are set to 1. This is 255. And then if we try to go further to 256, this is a number that requires 9 digits. And because we only have 8 bits in a byte, it is impossible to fit this number into a byte. So this digit is then lost. When we have a byte in a computer and we keep increasing it, then when we try increase number 255, we are going to go back to 0. So this is a cyclic structure. And we can also go in the other direction. When we decrease number 0, then we are going to get this number. And we can look at it as if this was number -1. This is another possible interpretation. So let's separate it from the first one. Then this is going to be -2 and so on. In case of this interpretation, we also need some kind of boundary to be able to tell when a number is positive and when it is negative. A simple way to do it is to look at this highest digit. When it is still 0, then we are going to look at the number as a positive one, but when it is 1, then we are going to look at it as a negative number. So here, the highest possible positive number is going to be this one, 127, and here the lowest negative number is going to be this one, -128. And positive numbers in this range are common to both interpretations. When we are adding or subtracting such values, both interpretations seem to work nicely. For example, if we subtract 1 from 255, then we get 254. But this can also be viewed as -1, which after subtracting 1 becomes -2. There are several ways of explaining these regularities, but the one that I find the most fruitful is through the theory of two-adic numbers. What is a two-adic number then? Well, it looks a lot like a binary number, except it can have infinitely many digits. For example, let's take these two numbers and make them infinite. We do this by adding infinitely many zeros on the left side. And there is really nothing special about it. This is just a binary representation of a number, and we simply make it infinite by appending zeros. However, we are also allowed to make numbers like this one, which is infinitely many ones. Let's try adding these two numbers together. What is the result going to be? We add 1 to 1, so we get 2, which is 0, and 1 goes to carry. So again we get 1 plus 1 from carry, so this is 0, and again we have 1 in carry. And this continues. And because we have infinitely many zeros here and infinitely many ones here, then we are going to get zeros all the way up to infinity. We are never going to get rid of this carry bit, but it is going to escape to infinity. So this result is in fact 0. And therefore this number is -1. How does this work? Well, I'm going to get to the math later, but for now it suffices to say that with two-adic numbers we operate under a different metric, one that allows us to compute things like a sum of all powers of 2, which would normally be disallowed because this would grow to infinity. And this is in fact the same number as this one, because when we have all digits set to 1, then this number is simply the sum of all powers of 2. And since we are allowed to compute this sum, we can also rearrange it. I'm going to write it this way. Because 2 times 1 gives us this 2, 2 times 2 gives us this 4, and so on. But this sum here is also the same sum as this one. So if we move this one to the right side of the equation and we move 1 to the left side, then we get -1 equals this sum. So it is quite easy to prove that this number is indeed -1. And since we are allowed to operate on such sums, we can construct any sequences of digits and do addition with carry or subtraction with borrow, except that we may need to carry or borrow indefinitely. Let's take a look at another number. Let's try another trick. Take any number, perhaps something like 5, and try inverting all the digits. So we flip zeros to ones and ones to zeros. In the assembly language notation, we would call it not 5. And let's take a look what is the sum of these numbers. You can see that all the digits that are set to 1 just fall into holes into the other number. So we do not have carry anywhere, and all digits of the sum are simply 1. So this sum must be -1. And this is true for any numbers, so we can just write that x plus not x is -1 in general. This also means that not x is -x -1. So, for example, not 0 is -1, not 1 is -2, not 2 is -3, and so on. We know that the non-negative numbers have only finite number of digits, so they all have only zeros starting from some point. And therefore, when we invert digits of such numbers, then the numbers that we get are going to have only ones starting at some point. So all negative numbers have the infinite sequences of ones, where the positive numbers have infinite sequences of zeros. And this brings us back to the computer representation of numbers. For example, when we have just 8 bits, then we are only able to store this portion of a two-adic number. And you can see that the highest bit, the sign bit, is the same as all the digits that are above it, at least for the numbers that fit into this range. On the other hand, when we have something like an unsigned number, for example, this would be a number 255, and then we need it to have all the higher digits be zeros. And this is the idea behind zero extension and sign extension. For example, on x86 architecture, we have instructions like movzx and movsx. We use these instructions to extend the number to fit into a higher number of bits. And when we use movzx, this is for unsigned numbers, then it fills the upper bits with zeros. And when we use movsx, which is for signed numbers, then it takes the signed bit and fills all the upper bits with copies of this signed bit. So when the number is positive, the signed bit is 0, then the upper bits are filled with zeros, and when the number is negative, the upper bits are filled with ones, the copy of the signed bit. And this simply can be viewed as extending the window through which we look at the two-adic number that is behind this. Another pair of such instructions is SHR and SAR. The first one is for the unsigned numbers, and the second one is for the signed ones. What these instructions do is shift all digits of a number to the right. And then we are simply decreasing the corresponding powers of 2. So this is the same as dividing the entire number by 2. Let's look at specific examples. When the number is odd, like here, then the lowest digit is going to fall out of the number when we shift everything right. It falls into negative powers of 2. And the CPU is storing it into carry flag, so it is not entirely lost. But for now, we are just going to assume that the numbers are even. So this is -2 or 254, depending on the interpretation of this value. And now when we shift this to the right, this digit is lost, and we need to insert a new digit here. When this is unsigned interpretation, then we know that all the digits above it were zeros. So we should insert a 0 here. On the other hand, when we shift a signed number to the right and we use SAR instruction instead, then this digit that we need to insert here should be the same as all the digits here above, which are copies of the signed bit. So these two instructions use different methods, zero extension or sign extension, to determine what the new bit should be. We also have the SHO instruction to shift left, and in this case there is only one instruction because we are simply looking at the lowest digits of the number and shifting them to the left. It does not matter what the upper digits are. So when we shift this number to the left, we need to insert a new digit here. We always insert 0. And we have a single digit that has fallen off the number. The CPU is storing this digit into carry flag. This flag can help us detect that an overflow happened. In the unsigned case, when we treat the result as an unsigned number, then we expect that all the upper digits are zeros. So when carry flag is not 0, then we know that we have something non-zero in the upper digits, and then this result is no longer a correct representation of the entire number. So in the unsigned case, we have an overflow when carry flag is set. As for the signed case, then all the upper digits are the same as the signed bit of the original number, and the signed bit of that number is now in the carry flag because the signed bit has been shifted out of the number. So all the upper digits are the same as the carry flag. And we have some result. Now when we look at this result as a signed number, then we look at the signed bit, and this bit is set to 1, so all the upper digits should be 1s, and they are, so there is no overflow in this case. We would have an overflow only if the signed bit of the result would be different from all the upper bits, which are the same as the carry flag. So in the signed case, we have an overflow when carry flag is different than the signed flag. This is the flag where CPU is storing the sign of the result, which is the same as the highest bit of the result. The CPU also has a special flag for this purpose, overflow flag. Let's test it. Let's take this number, put it into a register and shift it left. We can take it quickly into a debugger. Now we have executed the shift instruction, and the carry flag is set, and the sign flag is set. They are the same value, so there is no signed overflow, and the overflow flag is 0. And now let's discuss addition and subtraction. With unsigned numbers, this is quite simple. So let's take a look at some 8-bit unsigned numbers and add them. This is a standard addition with carry. So we have 1 plus 1 is 0, and 1 goes into carry. So next we have 1 plus 1 plus 1 from carry, which is 1, and 1 goes into carry, and so on. We never have more than 1 in the carry. And finally, we are left with a single digit of carry, which is stored into carry flag. But then we also know that the unsigned numbers are expected to have all the upper digits zeroed. And when we have something non-zero in the carry flag, it modifies the upper digits. So the upper digits are no longer zeroed in this case. And this indicates that this number is no longer a correct representation of the result, because this number treated as unsigned number has all the upper digits zeroed, and the correct result has something non-zero in the upper digits. So this is an overflow. And similarly, in the case of subtraction, let's take this number and treat it as unsigned and subtract this one from it. So now we have subtraction with borrow. We keep borrowing, and we are left with final borrow that is stored into carry flag. And this borrow does in fact translate to all the upper digits being ones. So again, if we treat the result as an unsigned number, then we treat it as a number that has upper digit 0, and this is not the correct result of this operation, because the correct result has something non-zero in the upper digits. And with signed numbers, this gets more interesting, because then we may have something in the upper digits that we need to add carry to. The upper digits are the same as the signed bit of the number. All ones here and all zeros here. Then we need to add the upper digits together with carry. In this case, this is like adding -1 plus 1. So the result is 0. To analyze when the overflow happens, we need one more observation. The largest positive number that we may get as a result of addition is when we take the largest positive number that we can represent as signed and add it to itself. This is the same as multiplying it by 2, so just shifting left. And in the negative range, the lowest we can go is to take the lowest negative number and multiply it by 2. This indicates that for positive numbers, the 9th digit is always going to be 0, and for the negative ones, it is going to be 1. And so we only need to know this 9th digit of the result, because all the digits above it are going to be the same as it. And how do we compute the 9th digit? Well, this is the sum of these two digits and the carry flag. And this digit is the same as the signed bit of the first number. Let's call it sign 1. And this digit is the same as the signed bit of the second number. So let's call it sign 2. And then the 9th digit of the result is simply sign 1 plus sign 2 plus carry. And this is the true sign of the result, because all the digits above it are the same. So for the overflow to not happen, we need it to be the same as the sign bit of the result, because the result is interpreted as a signed number, so it needs all the digits above it to be the same as the sign bit, and all the digits above it are the same as the 9th bit, which is this true sign. This is for addition, and for subtraction we would have sign 1 minus sign 2 minus carry, which is a borrow then. This is the sign flag, just for clarity. And what is interesting is that these two conditions are in fact one and the same. Because, as you may know, when we are operating on single bits, then the sum operation is the same as the subtraction, and this is the same as exclusive OR. Therefore, we can rewrite this condition as simply S1 XOR S2 XOR CF equals SF. And with XOR we can also easily move things around, because it works as both plus and minus. So when we subtract SF from both sides of this equation, we get S1 XOR S2 XOR CF XOR SF equals 0. We have no overflow when this equals 0. So when this equals 1, we have overflow. So we can take this simply as a definition of overflow, and this should be equal to the overflow flag. And we can also rearrange it either this way or this way. This last form is nice because what we have here is the true sign of the result. This is the 9th digit, which is the same as all the digits above it. And we can see that the true sign is the same as the sign bit as long as overflow is not set. And it is the opposite of the sign bit when the overflow flag is set. You may recognize that this is the value tested by x86 instructions like JL or setL or CMOVL. That's because this is the actual sign of the result of addition or subtraction. So testing this value simply checks whether the result is a negative number. Let's make another quick test. This time we are going to take these two numbers and add them. And then perhaps also set register CL according to this condition. The carry flag has been set. First sign was 1, second sign was 0, so this plus carry gives us 0 as the actual sign of the result. And also the sign flag is 0 and the overflow flag is 0, which also gives us information that the sign of the result is 0 in reality. And therefore this condition is not met. Here I end the first part. I'm going to discuss multiplication next time. Thank you for watching.